Okay, hi guys, my name is Lucy, this is Caleb and this is Emily, and today we're representing Team Sheffield from all the way across the pond, the UK. So our device this year, our project, was to create an open source microplate reader that is 1, cheap, 2, uses off-the-shelf components, and 3, can use Wi-Fi to send data to the cloud. Now, initially, our project was focused on creating a device that could record bacterial growth in the presence or absence of antibiotics. This would help healthcare professionals make more rapid decisions about what antibiotics to give to patients. This means that less unnecessary antibiotics would be given to patients, and therefore it would help fight against AMR. But when we started working on our project, we realized about this open source movement and decided to take a step back from AMR and instead do something even bigger. So our presentation today will have 3 parts. First of all, our motivation to why we did this project. Then Caleb will give a breakdown of the device, and then Emily will give a run through of all of the applications of our device. So I've mentioned this term open source already. What exactly is open source? Open source used to refer to software who's had its source code available to anyone. This means it was freely available for anyone to use, as well as customizable by anyone else who wanted to customize it. Here are some examples of some open source software. You can see at the top there's Mozilla Firefox. The penguin there is Linux. It's a bit like an operating system like Windows. And this cone here is VLC, which is a media player, and which, if you haven't used before, you definitely should be. So, free open source software. Obviously we have a lot, but what about free open source hardware? Are we able to make designs and release these designs so that they're freely available for everyone to use, so that they can make a device just like we have made it? Well, 30 years ago, this would have been very difficult, because machining parts would have been very expensive to make. However, with new, cheaper processing techniques such as 3D printing, you can now make an open source hardware project for a lot cheaper. In fact, you can even 3D print your own 3D printer. Printception. Okay, so here's an example for you. This guy on the screen here is Professor Pierce. He runs a lab in which he tests how well his sensors can turn light into electricity. To do this, he used a machine where he shone some light onto the sensors. This machine could change filters using a changeable wheel that was incorporated into the machine. On one poor, fateful day, this change wheel broke, and so he contacted the company where he got the machine from. However, the company did not supply replacement change wheels, so they asked him instead if he would be okay with paying $2,500 for a new wheel, and well, he had to wait 5 months until it arrived. Something you guys might have experienced if you've ever had an iPhone. But of course, he didn't want to pay that much, and he didn't want to wait that long. So instead, he did something different. Okay, so I've cheekily borrowed one of his slides from his presentations, and you can see the guy in the middle there is a high school student who he hired to help build an open source changer wheel design, which you can see on his screen on the left of the slide there. Professor Pierce then 3D printed this open source changer wheel on his open source printer. In the end, it only cost him around $50 to make a new changer wheel. So not only did he save a lot of money for his lab, but he also helped solve any future problems that lab might have with any of the changer wheels. So that's one way that open source can be useful. But here's another way. Funding in science. So the way it works is that 10 people will put their life's work into an application. 1 out of 10 people will get the grant. However, the other 9 people will be left sad and broke. 5 years later, that one person is still very happy. He's had a lot of research and a lot of papers come from his grant, whereas the other 9 people are still left sad and still left broke. So what if we could change this model? What if instead we prioritize giving the grant for people who focused in open sourced hardware? Yes, in year 1, you'd only get 1 out of 10 people being happy. But then 5 years later, his open source hardware could be spread throughout the scientific community so that they can actually build the equipment and use it for their own experiments. They would also be able to build and design improvements on the equipment for future uses. Of course, this is a much better way of funding in science, and one that we strongly believe in. This is why we wanted to focus on building an open source hardware project. To do this, we've uploaded instructions on our wiki on how to build it. To do this, we needed the device to be cheap. We were hoping for under £100. We can use off-the-shelf components and intelligent software so that people can regularly update the device. We also wanted the device to be portable so that it can be taken and put into places like on a shaker, or perhaps even used in the field. This would allow our device to be used in a wide range of broad applications, such as research, diagnostics, and teaching. So how exactly does our device work? Well, there's 3 main parts. At the top there, you can see the light source. In the middle is the well plate where we put our sample, and at the bottom are the light sensors. Now, light will shine down from the light source onto our sample. If there are a lot of bacteria in the sample, then only a small amount of light will hit the sensor. And if there's only a few bacteria, then a lot more light will hit the sensor and we can record that change. I'll now pass on to Caleb, who will give the nitty-gritties of how the device works.
So, thank you, Lucy. This is our device. It consists of a plastic casing containing the light source, well plate, and sensors. So, when choosing a light source, we considered 3 main components. Those were LEDs, halogen bulbs, and EL panels. We finally chose LEDs for 3 main reasons. Firstly, LEDs are cheap. They allowed us to keep the entire cost of the device low. Secondly, LEDs are really easy to control. By changing the voltage across them, we can easily adjust the brightness, and they're far brighter than EL panels. When we tested the EL panels, they weren't even bright enough, they didn't produce enough light to even be picked up by our sensors after passing through the wells. Thirdly, when using halogen bulbs, we realized that the light was not nearly diffuse enough to enable consistent readings across our plates. But by using a matrix of LEDs, we ensured that readings were consistent and our results could be reliable. So, well plates. Initially, we started by using a standard 96 well plates. But then, to show the maximum accuracy of our device, we decided to use deep, narrow wells. This increases the length of light path traveling through our sample, and increases light attenuation according to Beer-Lambert's law. Sensors. We settled on photodiodes as our sensor, as we thought they provided the best compromise, as they're far cheaper than photomultiplier tubes, but also far more sensitive than light-dependent resistance. So after choosing some components, we then started the process and 3D printed and laser cut the casing for our device. That keeps the light source, well plate, and sensors all in line. This is our device here, isn't it beautiful? We then made the files for this available on our wiki to ensure that it's kept open source and available for the scientific community to use. So here it is, a truly open source device coming in at under £100. So I'm now going to talk about how and why we use multiplexing to read data from our device. So if you can imagine each circle as a photodiode connected to the photodiodes around it in a grid via wires. We needed a way of isolating one diode to read. So at the moment, all diodes are very high resistance, so not much current can get through, and no data on how much light is hitting each sensor can be read. But we use 2 multiplexing switches to solve this problem. The first one goes down each row and sets it to a low resistance so a current can get through. And the second one goes down each column and connects it directly to our microcontroller so that data from that diode can be read. So it goes along until all data has been read in that row, and it goes down each row until the whole well has been read. The whole well plate has been read. But by using this approach, we don't need 96 wires connecting our device, connecting our well plate to our microcontroller. We only need 1. So I'm now going to talk about data collection. So after the individual voltages have been read, we use the data sent to the cloud via a server known as ThingSpeak. ThingSpeak is an Internet of Things platform that works directly with our Arduino microcontroller to send data to the cloud without any need for extra hardware. ThingSpeak also works with MATLAB, so we can do real-time analysis using MATLAB all in the cloud. For example, we decided to plot the log of our data in real time to allow for easier analysis and interpretation. MATLAB is also able to interface with other hardware so that our device can seamlessly integrate with other labs. So data processing. Another advantage of MATLAB is that it's highly powerful and an industry standard. This means that we can perform real-time data processing right in the cloud. As our intended user as we have a wide user base, we use MATLAB so that individuals could write their own code tailored to that application. For example, Diagnostics labs could write code that predicted the chance of a sample being susceptible to an antibiotic, whereas a research lab may wish to implement machine learning models that could predict what family the bacteria belongs to. So over summer, we were able to successfully run overnight tests and send our data to the cloud without us being there. We then used this data to produce the growth curve you can see on the right, and compared it to data we collected with a real well-put reader. One clear advantage of our device is that we can take data in increments as low as 15 seconds. This is particularly applicable when we think of machine learning modules that MATLAB contains, because they can really take advantage of these data points and perform experiments that simply wouldn't have been possible 5 years ago.
All right, so I'm going to take you through some of the applications of our device. So we've now designed an open source microplate reader, but who could use this amazing device? We've considered its use as a tool in research, medicine, and teaching. So as a research tool, this is Victor. Now, he belongs to a reasonably well-funded lab at our university. In fact, he's so cutting edge, he came with his own floppy disk tutorial. Now, here's Victor again. He's great, but what's that? You can't see him clearly enough? How about now? Still not big enough? Getting better? Okay, that's enough now. But anyway, point being, every time we wanted to use Victor, one of our team members would have to plate out a sample, and she and Lucy would have to trek up 4 flights of stairs from the teaching lab on the ground floor in order to take a measurement using Victor, take the plate out, go along the corridor into the incubator, put it down, leave it, go back downstairs, and continue work. But they'd have to do this repeatedly over the course of the day. So this would take a huge chunk of time out. You could only do up to 7 measurements every day because you can't go in the lab outside of 9 and 5. So it generally wasn't working for us. So compare this to our device. What this does is you take your plate, you put it in the device, put it in the incubator, and just leave it. You can get all your work done, no fuss. Now, this allows autonomous data collection. Just let the results upload automatically. You can do overnight experiments, just leave it to run. So this improves your workflow, your costs, and your data quality. Now, initially, our goal was to use it as a diagnostic tool in order to fight antimicrobial resistance, or AMR. So, to do this, we took a couple of steps. Started with step 1, which was speaking to scientists at different microbiology labs from some of our team members' own home countries. Now, we took these ideas, sort of built them into our device, and then we took it to step 2, speaking to healthcare professionals at universities in Sheffield and Liverpool, and PreventX, which is a diagnostics company. And we sort of took a couple of their ideas, such as encryption for data transfer, and implemented them into our device. And we just kept doing that, reiterating the process. Now, this is our main competition in diagnostics, is Phytech 2. Now, it does have several problems. First of all, it's huge. That thing is covering the entirety of that desk. It also costs a lot of money. The lab we spoke to in Sri Lanka couldn't afford one, and the lab we spoke to in Poland had one, but they would only use it for their most critical of patients. When they did use it, this is a pre-made sample plate of antibiotics. Now, they just take the sample, plate it out on this, put it in the device, and leave it to run. That seemed pretty handy to us, so we were inspired by that, and we figured if our device was going to be used as a diagnostic tool, we should provide it with pre-made well plates, typically in 96 well plate form, and you'd add specific amounts of each antibiotic in powder form, so the user only needs to simply plate out the sample, put it in the device, leave it to run. Now, we did include the encryption software that was advised by Preventex. This was developed by Caleb. Now, we then went on to consider it as a teaching tool. So this is where we spent most of our summer, in this teaching lab, and it's for about 100 students during term time. Now, we have a lot of equipment here. Here's some of the more typical ones. You've got your microcentrifuge there, your vortex mixer there, and a spectrophotometer at 4,000 pounds. So, we spoke to the lab manager in this lab and sort of asked her how our device could be of use to her as a teaching tool. Now, for her, she gave us the example that a spectrophotometer costs 4,000 pounds. Now, for her lab, that's a lot of money because you need one for every 10 students. So that's 40,000 pounds in total, just to be equipped for this lab practical. Compared to our device could be provided, you get 10 of them easily for 1,000 pounds, which is 40 times less. I mean, it's still more in dollars, but it's 40 times less in pounds. And we then continued to talk to her about different ways we could adapt the device. One way that she would prefer is if filters could be provided. Easily, we found ours quite cheaply. So more filters provides more wavelengths for the device, which then results in more experiments for use in this. So, to summarize, we've brought to you an open source microplate reader. The specs are on our wiki. Feel free to check them out. They're available for future iGEM teams as well. It's cheap at under £100, and it's also got a broad range of applications across research, diagnostics, and teaching. We'd like to thank everyone and invite the team up on stage for the questions.
So, you built your own encryption software for handling HIPAA-protected data. What sort of analysis did you do of the encryption method that you had to determine how it compared to existing state-of-the-art encryption methods? Because building your own encryption method is typically a recipe for having your code, all of your data owned stored by random people.
So I built this encryption software based on a discrete mathematical model after speaking to labs about patient confidentiality. I spoke to various people in the university to see what standards would have to set to do that sufficiently. But I can talk about frequency distribution analysis and stuff I did to ensure that my encryption software was good enough. But the main advantage was that the method I used wasn't used by many other people. So people trying to break that encryption wouldn't be able to break it in this way. I'm not saying that my encryption software was particularly fantastic. It's just that people aren't working on it because other people aren't really doing it. Does that answer your question? So
security by obscurity, which essentially works until the point where your stuff becomes really cool and lots of people use it, and somebody says, that's not obscure anymore.
Yeah.
Especially with an open source system.
Yeah.
Speaking of that, by the way, I very much laud the embrace of open source. One thing that I was a little bit unclear on, I couldn't find on your wiki. What's the license that your hardware specs are available under?
We didn't actually publish specs and instructions. There are certain open source websites for that where you can upload those kind of designs. We haven't done that yet. We'd be happy to hear about all the critique and maybe adjust everything, and maybe then we'll consider uploading our instructions and design.
A thing that you may wish to consider, you don't necessarily have to put it somewhere else to put an open license on it. So, for example, there's free hardware licenses, and for documentations, Creative Commons has a whole range of open license options. Then, when the wiki unfreezes, you can just put a stamp, on the materials that says, this is available under this open source license and that open source license.
We'll be very happy to market it once we address all the comments and critique. Yeah.
Thank you.
Thanks very much for a fantastic presentation. You did really well, very exciting project, and I look forward to the poster session as well. So yeah, I think with IoT applications, security becomes a bit of a risk, and especially when people deal with data, it could be an important point to consider. So one thing I was wondering, have you guys considered point-of-care diagnostics with your device? Because you could essentially power up the Wi-Fi with a mobile device and then hook that up with cloud analytics. And also, if so, how much can you miniaturize the device?
Okay, so we went to one of the hospitals, and one of the people there spoke to us about possibly using it sort of in setting scenario with patients directly. The problem we have with that is obviously the turnaround time whilst you wait for bacterial growth, we found was 6 to 8 hours for our device. But the issue they had with that is that's obviously not a fast turnaround in, for example, the NHS. So you couldn't keep a patient there all day. So point-of-care diagnostics became a little bit sort of, it wasn't really what we were aiming for, just simply due to that. It could be considered, but our device has been sort of miniaturized from the prototype. But I think possibly it depends. We're limited by the size of the plate as well.
Thanks. One more.
Yeah, fantastic project. I would probably be a user of this kind of tool in my own work. Something that I battle with constantly is background noise. And I wondered whether you guys had any consideration about background noise and what you did in your project to try and mitigate some of the effects of this problem.
So background noise is definitely an issue at points in our projects. There are a few things you can do when we built it, and if we go back, we would make some changes. Things like separating digital and analog signals, because digital signals are very noisy. But one of the main advantages of our device is that we can take a lot of data, and using all those data points, that means that when we smooth data, it smooths them much more accurately than when you have fewer data points, if that makes sense. So often we found that even though we did have a lot of noise, because we were taking data very, very, very frequently, the noise wasn't so much of an issue as if we've been taking it less frequently.
Thank you.
Thanks very much, guys.